So last week we covered series circuits, and I hope you found it pretty easy. I don't think they're too complicated. This week we're going to cover parallel circuits. Parallel circuits are a little bit more complicated, mainly just how you calculate the total resistance. But overall, they're not too bad either. Next week, though, comes series parallel. And the thing about series parallel circuits, so circuits that have both series and parallel, is that we break them into parts. And so we really only do the series and the parallel separately, but you need to understand both of those methods or it's going to look really complex. So make sure before the end of this week you understand both series and parallel circuits very well, and you'll be in good shape for honestly the whole rest of the course. You'll also see that pretty soon I'm going to stop using slides and mainly go to working out problems with you since we'll be working with bigger circuits. Before we get there though, let's look at parallel circuits. So this is a parallel circuit that I have on the screen. Here's how you test if a circuit is parallel. Look at the top of something like a resistor, and if it is connected to another resistor's top with nothing in between, so meaning no resistors between the two tops, and it's connected on the bottom to that same resistor with nothing else in between, then we would say those two are in parallel. In the case that I have on the screen, notice that all four of these are connected at the exact same spot on the top with nothing in between them, and they are connected on the bottom at the exact same spot with nothing in between them. So we would say that these four resistors are in parallel. Let's look what that means. So a parallel circuit is one in which all of the components are connected in parallel with each other. For example, the one we have on the screen. And just like all circuits, notice that it still has our source, right? Something to make the electrons move. It has a load, in this case that's everything to the right, and it has a closed path, meaning that it's fully connected all the way around. The difference between this and a series is that notice there are more than one path the current can take. So remember, let's do our series test on this and see how that would go. So I start here and I trace it with my finger. I come this way and notice I don't have to go through R1. Some of the current will go through R1, but some will continue going this way. That choice is what tells us it's no longer a series circuit. And again, we know it's parallel because the tops here are connected and the bottoms are connected. And so that's how we can easily identify this as a parallel circuit. Because these are in parallel, notice that their voltage has to be the same, right? If I were to put my ground here, that would mean this bottom wire is at 0 volts. So everywhere I'm drawing here is at 0 volts because it's all connected and there's no devices between. Remember, the voltage across a piece of wire has to be the same everywhere. If we look at the top, if this is 0 and I go up by 5 to get to here, then this whole top that I'm drawing kind of squiggly lined is at 5 volts. And so notice the difference across each of these resistors from here to here has to be the same 5 volts. And so this is our first rule with parallel circuits. For parallel circuits, all of the voltages have to be the same. Remember, with series circuits, it was the currents had to be the same. So it's kind of like the opposite with parallel. And so if I were to take my voltmeter and measure across each of these devices, I would measure the same 5 volts of pressure across each of them. Now remember, last week we had Kirchhoff's voltage law, and it said that if I start at any point and I go around the whole circuit, by the time I get back, if I add up all of the rises and all of the drops, that has to equal 0 volts. With Kirchhoff's current law, it says that if I'm looking at a connection on a wire, so a node, that all of the incoming current has to equal to the outcoming current. So if I add up all those currents, they have to equal 0. And what I mean by that is, before we get to currents, let's pretend like this was a street intersection. If I had 5 cars driving down this road, and I had 3 cars going this way. So we add up all the cars, and there are 5 that go this way, and 3 end up going this way, and this is the only other exit, then that means we must have 8 cars leaving this way. Same thing is true with current. If we were to test this and say that we have an overall total of 4 milliamps going in this direction on this wire, and 2.5 milliamps coming in this direction on this wire, notice there's nowhere else for them to go but here. And so again, if I have 2.5 milliamps entering, we would say that's entering the node, and I have 4 milliamps entering the node, then I must have 6.5 milliamps leaving the node on this wire. And again, the reason is because it has to go somewhere. It can't just stay in the middle of the node. And so you guys try this example, and then I'm going to do it with you. Okay, so this is the one we don't know. We don't know which direction it's going in. And so what I'm going to do is I'm going to look at it from this node's perspective. Incoming, we have 4 milliamps. No, we have 2.5 milliamps. Leaving, we have 4 milliamps. Remember, both of these sides have to equal each other. At the moment, we have many more leaving than we have coming in. And so, 2.5 milliamps plus what would equal 4 milliamps? Well, 4 milliamps minus 2.5 milliamps means that we must have 1.5 milliamps, and it must be incoming, since that's the side that's less. And so the current must be going this way, and it must be 1.5 milliamps. Now, there's another way that you can do this as opposed to making columns, since that takes a long time. What we can do is we consider currents that are entering the node to be positive and currents that are leaving the node to be negative. If I do that, I can say that we've got 2.5 milliamps entering, I've got negative 4 milliamps leaving, I have some current that I don't know, and all of this, remember, entering minus leaving has to equal 0. And so if I solve this equation, it's going to give me the answer. And so we can see I is equal to, I'm going to move this to the other side so it becomes negative 2.5 milliamps. I'm going to move this to the other side so it becomes positive, plus 4 milliamps gives me 2.5 milliamps. And since it's positive, it must be entering. So however you like to do it, either way works. And this is explaining just what I just said. Basically, put a positive sign if it's entering, put a negative sign if it's leaving, and the total has to be equal to 0. So Kirchhoff's current law works not just at one spot, but no matter how big we make that node, it still has to be true. So notice, let me do this first. The example is doing it with letters. Let's use real numbers, because I think that's the easier place to start. Let's say I calculate the current, and the total current in the circuit is 20 amps. That would mean, since that has to come this way, it has to be here, the current here is still 20 milliamps, because all of it's going in that direction. If I1 is equal to, let's say, 4 milliamps, meaning that 4 milliamps chooses to go down this path, how many must be going this way? Well, again, if you had 20 cars driving down that street and 4 made a right turn, that would mean that there has to be 16 milliamps going this way. If down this path we solve for it, and it turns out that 2 milliamps goes there, and I had 16 entering here, that leaves 14 milliamps to continue going this way. Finally, if 10 of those milliamps come this way, that would leave just 4 milliamps to go the final path through R4. And so this would be 4 milliamps. Notice that if I add this, plus this, plus this, plus this, that has to equal 20. Because again, if we did Kirchhoff's current law, we have 20 milliamps entering, and so leaving down these paths, we also have to have 20 milliamps leaving. And so that's what Kirchhoff's law is trying to tell us here. Notice that IT has to be equal to I1 plus I2 plus I3 plus I4. We could write other things too, right? Like I know I2 has to be equal to IA minus IB, meaning the number of cars going this way is whatever the number of cars was going this way minus the amount that went this way. And so again, the only purpose of this is to show you how Kirchhoff's current law works. It works at just one node, like looking at a spot just like that, but it also works if I group a whole grouping like this. Entering has to be the same amount that eventually leaves. So remember how we calculated the resistance for resistors in series. For instance, if I had this, this, and this. All of these are in series, and so if I wanted to know the total resistance, I would have R1 plus R2 plus R3. For parallel circuits, unfortunately, it's an uglier formula. There are two formulas you can use. Let me jump ahead and then we'll come back and do it together both ways. So you can enter the formula this way on your calculator, which is, I think, easier, or you can enter it this way. The problem with this way is that you have to use a lot of parentheses and it can be really confusing to enter on the calculator. So this is the way we most often do it. Let me show you on your calculator how to do this. So let me bring up the calculator and we'll solve the problem at the bottom. So almost all of your calculators are going to have a 1 over x button. This is what we want to use to do this. And here's how we do it. I have 3 resistors in parallel here, so I'm going to enter it one by one. First thing I want to do is type in 680, so 680. I then want to hit the 1 over x button. That basically gives us the reciprocal. So I hit it once. I then do plus 1.5 e to the 3, and I hit 1 over x again. Plus 2.2 e to the 3, then I hit 1 over x again. Now this is the important part. After you've done all 3, hit equals 1 time. This still isn't the answer because notice we have to do 1 over RT to get the final answer. So we hit 1 over x one more time. That's our final answer, 386 ohms. We'll do some more problems like this again at the end. And so we get 386. So at this point, instead of explaining to you how to do parallel circuit analysis in theory, let's just jump right into it and do some problems. Okay, so before we jump into doing circuit analysis on parallel circuits, let's try one more example of Kirchhoff's current law. So again, I've created a drawing that's not so great of a circuit node, right? So what we want to do is we want to figure out what must be this current here. And so what we're going to do is we're going to look at it from the perspective of this node. And so again, remember we want to treat incoming. So incoming is positive, outgoing is negative, and both have to equal 0. So let's do that. I'm going to start here and work my way counterclockwise so I don't miss any. So we have 6 milliamps. Notice it's incoming, so I'm going to set it positive. I then have 2 milliamps here leaving, so it's going to be negative. I then have the one I don't know, so I just do plus I because I don't know what it is. Finally, over here, we have 5 incoming, so I'm going to set it to positive. And then last but not least, we have this 3 milliamps outgoing, so I set it negative. I then set this whole equation to 0. Now all we need to do is solve for our unknown I. So remember, when you take a value and you move it to the opposite side of the equation, it flips its sign. So all I'm trying to do is get I by itself. So if I rewrite this, I have I is equal, when I move 6 milliamps to the other side, it becomes negative, plus when I move 2 milliamps, it becomes positive, minus 5 milliamps when I move it over, and plus 3 milliamps when I move it to the other side. So like I said, all we did was we moved this one here, we left it on this side, we moved each of these to the other side of the equation. Now I just need to solve this, so I have I is equal to, we have negative 6 plus 2, which gives us negative 4, minus 5, which gives us negative 9, plus 3, which gives us negative 6. And so the final answer I get here is negative 6. Of course, you could do this on your calculator if it's easier. Now, since we get negative 6 milliamps, that tells us that the magnitude of this one needs to be 6 milliamps, and because it's negative, it must be outgoing. So this arrow was actually drawn correct. It has to be 6 milliamps outgoing, because that's the answer we got. Alright, now let's move to circuit analysis. So again, the first thing we want to do is determine, is this series or is it parallel? It can't be series because notice that we have a choice here. We can confirm it's parallel because notice that the top touches, the bottom touches, and in fact even with the power supply. And so now that we know it's parallel, we immediately know a few things. First, I'm going to pick my ground here. Because this is 0 and we go up by 12 volts from here to here, we know that this top wire is at 12 volts. So that means the voltage across this first resistor from here to here has to be 12 volts. Same with this one because it's parallel. So already I can answer those. I know that the voltage over resistor 1 is equal to 12 volts. And I know the voltage across resistor 2 is equal to 12 volts. I still don't know the current through resistor 1, the current through resistor 2, or the total current. So those are three things I still need to figure out. Notice though, for resistor 1 we know both its resistance and we know its voltage. And so, going back to Ohm's law, V is equal to I times R. I is equal to V divided by R, if we just divide both sides by R. And so for resistor 1, the current in resistor 1 must be equal to 12 volts divided by 1 kilo ohm. So if we bring up our calculator, we have 12 volts divided by 1 e to the 3, which gives us 0.012, and when we convert that to engineering notation, we get 12 milliamps. We can now do, so we can go ahead and write it on here so we keep track of everything. So the current going this way is 12 milliamps. Now we need to solve for this current, and so for I through resistor 2, we have 12 volts divided by 4 kilo ohms. And so if I again bring up my calculator, we have 12 volts divided by 4 e to the 3. We get 3 milliamps. And so this is an important point that I didn't point out during the lecture. Notice that current is going to mostly go through the least resistance. It always chooses to go through the least resistance it can. And so notice that when we had 1 kilo ohm, our current was 12 milliamps. When we had 4 kilo ohms, it dropped down to 3 milliamps. Now finally, so I can go ahead and begin to fill these out. We have 12 milliamps, 3 milliamps. For my I total, notice the current that's going this way. Well, if I have 12 coming this way, if we look at this node, and I have 3 milliamps going this way, that means there must be 15 milliamps coming in. And that's it. In a lot of ways, parallel to do the actual circuit analysis is even easier. Let's try just a couple more things to make sure we understand it. So let's get our total. So remember, our total, to get that, we have to use that equation. It's actually 1 over R total equals 1 over R1 plus 1 over R2 in this case. And again, I want you to pay close attention to how I do this on the calculator. So we do the first resistor, which is 1K, 1 e to the 3, 1 over x, plus 1, plus 4 e to the 3, 1 over x. Okay, I then hit enter, and then I hit 1 over x one more time. So we get that the total resistance is 800K. 800 ohms, rather. Now, at first this may seem confusing. Notice I had a 1K resistor and a 4K resistor, and my resistance is only 800 ohms. That's actually what it has to be. So here's a way to check your work. The total resistance always has to be smaller than the smallest resistor. And the reason is, think about it. If the total resistance were more than 1K, it would just always go down the 1K path and pretend like this isn't here. We can never add more resistance by adding extra resistors. The more paths we give the current, the more options we give it, the lower the resistance will become. And so again, your total resistance always has to be smaller than the smallest resistor. Finally, we can double check our total current number, right? Because remember that Ohm's law still applies. Remember, the source has to equal the total current times the total resistance. So if I try to solve I total this way, by taking our 12 volts and dividing it by our 800 ohms total resistance, notice that we'll get the exact same answer. 12 divided by 800, we get 15 milliamps, which is exactly what we got working out the problem. So we've fully checked our work multiple times, everything looks good. Let's try a more complicated one. So in this circuit I have 4 resistors. Again, we want to start by putting a ground. We want to verify that they're all in parallel. They all share the same top, and they all share the same bottom, so they must be. That means we immediately know that the resistance across each, the voltage across each of these is 12 volts. I'll write it on here. And so again, voltage in resistor 3, 12 volts. I resistor 3, we don't know. This is a good idea, by the way, writing everything you know about the problem down as soon as you start it. And again, I through 4, I through 5, and I through 6, we don't yet know. Okay, but we can, again, using our Ohm's law, V is equal to I times R, and so I is equal to V divided by R. We can solve for the current here, 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 and here. So for the first one, we have I in R1 is equal to 12 volts divided by 1K. Actually, we just solved that, right? What did we get for that? I don't even remember. 12 divided by 1E3, 12 milliamps. So we have 12 milliamps. So we know that we have 12 milliamps going down this path. I R2, we have 12 volts and 3K. Bet it's 4. 12 divided by 3 e to the 3, we get 4 milliamps. For IR3, we have 12 volts divided by, again, 3K. So it will be 4 milliamps. And finally, for R4, we have 12 volts divided by 5K. One last time, 12 divided by 5e to the 3, we get 2.4 milliamps. And so we have all of our currents now. Now the last thing that we need is we need to know what is the total current coming from the source. Well, it's going to be 12 milliamps plus 4 milliamps plus 4 milliamps plus 2.4 milliamps. Again, the reason is, notice if this is considered to be one node, I have IT entering and all of these leaving. And so if we add that up, that's 12 plus 8, which is 20. So 22.4 is our IT. Last but not least, let's solve for RT on our calculator. So we have 1 e to the 3, 1 over x, plus 3 e to the 3, 1 over x, plus 1 plus 3 e to the 3, 1 over x, plus 5 e to the 3, 1 over x. We hit equals, and then 1 over x one more time. And so we get 536, we'll call it. 536 ohms, which makes sense because it's smaller than the smallest. One last time, we can test our theory. So if I take our 12 volts and divide that by 536, you can see, what am I doing? Yep, we get our 22.4 milliamps. Notice it's slightly off because we rounded the resistance, but it's pretty close. So that's it for parallel. I hope you found this pretty simple. Like I said, by themselves, parallel is pretty simple. By itself, series is pretty simple. Make sure you have it both down though, because when we go to series parallel next week, we're going to use all of them. Contact me if you have any questions. Talk to you soon.